Okay, welcome to Remote Learning 8, and we're going to cover some things that we didn't cover in section 6.7 during Remote Learning 7, where I spent the entire time talking about modeling exponential functions, but we didn't get to modeling the logarithmic function. Now, regarding the exponential function, we saw that there are quite a few ways to do it, involving using a system of equations, rewriting the output as the natural log, and then using a linear model converted back into an exponential model. That was more difficult. And then we also saw that the calculator can be quite helpful, and we used a exponent regression. Be careful with that one because there's also an exponential regression that involves the natural log, which depending upon the directions you may or may not want. Let's see, I misspoke there. The exponential does involve a natural log, it involves e. Okay, so today we will be talking about modeling with natural logs because we're going to be modeling the logarithmic function, and we're going to use the calculator. So this is going to be a calculator exercise, very, very similar to what we've always done in terms of working regressions. This is just going to be a regression where we'll use a logarithmic model. So just wrapping my mind around this problem, and as is true with most word problems, there's some extraneous information. In the end, we're just going to be grabbing the table, and there's very few things that are really important until you get to the end and they ask these extra questions like estimate the altitude when the pressure is 0.75 atmospheres. Okay, so without reading the rest of it, you can't really understand what to do. So here we go. So the atmospheric pressure decreases with increase in altitude, so-called thin air. As you rise in altitude, the atmospheric pressure decreases. At sea level, the average air pressure is 1 atmosphere. That is just like a way of setting the scale, so to speak, right? So since we live near sea level, we're like, okay, we're going to call that 1 atmosphere. Now it's measured to be this crazy weird number, 1.033 kilograms per square centimeter, but this is totally superfluous to the problem. We won't have to worry about it at all because everything is going to be measured in terms of atmospheres. All right, so the table shows the pressures P, here are the air pressures P, in atmospheres. That's making this completely superfluous, and I'm going to get rid of it. Okay, so the table shows the pressures in atmosphere. Here is sea level altitude 0, and there's 1 atmosphere of pressure. And then as you move up in altitude, then these numbers get smaller and smaller and smaller. Okay, so the table shows the pressures at selected altitudes, measured in kilometers, I might add. Use a graphing calculator to find the logarithmic model of the form, this case, altitude equals a plus b times the natural log of the atmospheric pressure. Okay, so here's the data. We need to find the logarithmic model that represents the data, and it's a calculator exercise. Once I have the model, then I'll go on to answer this question here at the bottom. Okay, so let's roll through the calculator use, and let's see, how is this thing currently set up? Looks like I'm in graphing mode, so that's not where I want to be. I want to be in apps statistics. So going into 2 variable statistics, and all right, again, as usual, we're going to be putting the data in here. So first thing that you need to think about is what's the input and what's the output. So if we look at this function, a and b are constants. They're not part of the table, right? P and h are our variables. P is the input, h is the output. So while the table shows these pressures at various altitudes, the way the formula is going to work is you're going to put in the air pressure, and then it's going to compute and tell us the altitude All right, so input, output. So I'm going to make this first column all of my inputs. And all right, so it looks like I've got 0.55 is the next one, 0.25, and so on. Let's just type these in. And I've got to delete that one, so let's just delete that guy. And while I'm thinking about it, delete that guy. Okay, so those were the various air pressures, and let me just double check those numbers. Okay, and then the altitudes. Okay, so I just want to make sure everything is correct. Okay, so there we go. I've got the C1 column and the C2 column, and if you're working on the Texas Instrument, you've got L1 and L2. And next thing I need to do is go to, remember, these three buttons play well together. We're right here. We go into plot. Okay, so that's fine. That's for reasons we don't need to worry about. And then we're going to go to symbol. And okay, so I've got C1 and C2, and I need to change my model to logarithmic. Right? We are working on a logarithmic model. And then let's just double check that it's got things written the way we want. Well, it is, but they've got, they've commuted around the plus sign, and then they've changed A and B to B and M. So, okay, we may not like the fact that they did that, but it is definitely the model. Okay, so then I can just go back to number, and I can go back to symbol, and it didn't change it. Bummer. Okay, so hit plot and go back. Okay, now I've got the numbers. Okay, so those are some pretty wickedly annoying numbers, but there they are. It looks like R, little a, is 0.86, and our B is negative 6.45. Okay, so 0.86 minus, and that number is 6.45. And then that's the natural log of the input, which is the air pressure. Okay, so let's see. That's working on the HP. And in terms of the Texas Instrument, then it's L1, L2 inside of stat. Then you got to go over to calc, also inside of stat, and find the logarithmic model, and then things will show up. All right, so then moving on to answering the question. The question is estimate the altitude when the air pressure is 0.75. Okay, so this is where that is our input. That's the air pressure. And then we need to put that in for our P variable and see what comes out. Okay, and then that is another calculator problem. And that turns out to be H equals, yeah, let's do it real quick. All right, so get that out of the way. And all right, so I'm going to go home, and it is 0.86 minus 6.45 times the natural log of 0.75. So 2.72 kilometers. Okay, and that seems pretty good to me in terms of just wrapping my mind around the data here. It went from 1 to 0.55 and kept diminishing, so 0.75 is somewhere in here. So then our answer should be somewhere in here, and it is. It's between 0 and 5. So all of that feels good. Okay, so this next example is the end of the chapter, and it is in this section that involves exponential and logarithmic functions, but it is actually neither of those, although it is related. This is called the logistic function, and I do want to show you it, although it's really going to be a calculator exercise for the most part. So I'm not going to explain like all the features of the logistic function. This one that looks like it's a fraction. Um, okay, but you can see that it's related in the sense that I've got an exponential decay scenario on bottom. And okay, so that's why they've thrown it in to this chapter 6 here right at the end. All right, it's a good problem. And let me just get us thinking about it. So you plant a sunflower seedling in your garden, and the height, h, in centimeters of the seedling after t weeks can be modeled by the logistic function. So here it is, h in terms of t. So number of weeks. Remember, e is a number, so that's not a variable. So that's number of weeks past, 0 weeks, 1 week, 2 week, 3 week. And then this models the height of the sunflower as the weeks pass. So part A is find the time it takes the sunflower seedling to reach a height of 200 centimeters. So let's make sure everything is, we got the right units. So we're looking at T is weeks, H is centimeters. We have a centimeter scenario, so that's good. And then our answer, we'll just have to call it weeks. We don't have to run into any unit problems. Okay, so for part A, I'll come over here. For part A, then we use the function. And what we know is the input is the number of weeks, and the output is the height, and our height is 200. So we have a complicated algebra problem to solve. Okay, so then I'm going to work on solving that. And one thing that I see in the problem is that the variable is on bottom of the fraction, so I don't like that. So I'm going to flip each side. And that's, taking the reciprocal of each side. And that is a totally legal algebra move. So that makes me feel a little better. My t is up on top. I can get rid of the 256 by multiplying each side by 256. So everything seems to be going smoothly so far. Okay, so unraveling this, the next thing I would do would be to subtract 1. And then divide everything by 13. All right, now I feel like it's time to go to a calculator and get that left side figured out. Okay, so let's see. I've got 256 divided by 200 minus 1. That is the numerator, and then that is divided by 13. And scientific notation here, so I'm going to move it back, so that's 12.022. All right, I'm going to call it 0.022. Moving the decimal twice, that'd be 2.2. Let's just double check that I did that right. Yeah, okay, so I rounded. Yeah, okay, I think that's probably fine. So, okay, I was going to change my rounding by one place, but I'll leave it like that. Okay, so then the next thing to do is, okay, I'm trying to get to t, so it's time to get rid of the e now. That's an old lesson. So we're going to natural log everything, and then this just becomes some other annoying decimal. But this becomes negative 0.65t. And then finally, dividing off the negative 0.65. So I have t equals, and then it's back to the calculator. So let's see. I've got the natural log of this 0.022, which was the previous answer. So now I'm just going to go and grab answer. So now it's more precise. Divided by negative 0.65. I type all that correct? Good there. And it looks that 5.9 is what I'm going to go for. 5.9 weeks. Okay, so great. We're at 200 centimeters after just about 6 weeks. That's just a more difficult algebra problem. The key thing would be this first move, I think, where I took the reciprocal of each side, bringing my variable that's on bottom back up. Okay, let's see. I'm thinking about this, and I know a lot of people in the room would like to use cross multiplying right about now. So I will point out that when you have a fraction equals a fraction, and I know this is a really complicated fraction, but nonetheless, it's a fraction equals a fraction. The cross products are equal. And then if you do that and divide each side by 200, you get right back down to this level. So you can do my reciprocal move, or you can do cross products are equal. All right, part B. Use a graphing calculator to graph the function. Interpret the meaning of the asymptote in the context of this situation. Well, you have to remember what an asymptote is. It's a line that the function pinches closer and closer and closer to, right? An asymptote. It's a imaginary line that the function vanishes towards. Right. So let's graph it. So graphing calculator. And I'm going to go to apps and function and type this guy in, which is 256 divided by this crazy 1 plus 13 e to the negative 0.65 times the variable. Did I do that right? I'm going with yes. Invalid exponent in number. Invalid exponent in number. Oh, I know what's going on here. They just like you to put a multiplication sign whenever you're working with e. Okay, so now you can pinch pull and find your way to the graph, and my guess is that when I plot this, it's not going to look too nice. Yeah, and it's giving me a little arrow that it's up there somewhere. So if I scroll and scroll and scroll, oh, I found it. Okay, but that doesn't look to be so great. It's like, all right, so let's get some insight in here. I'm at way up at 256, and let's see, I'm counted by ones here. That's what these hash marks are. Okay, so let's get a little better view as to what's going on. And okay, so that means I'm going to go to window, plot setup, and weeks, that's the input. So I'm going from 0 weeks out to 10 weeks, and we'll see what happens with that. And let's see, these are the various heights of the sunflower. So I'm going to go with 0, and we just saw that thing reached up to about 256. So I'm going to put 260 in there, and then see if I can get a good plot of this. Okay, so yeah, I mean, I know what's going on here. It's like you can actually see it, but it's zooming up super fast and then it's flattening out. So in order to see that better, let me go back into setup and change this so that it doesn't go out so far. I'm just going to have it go out to 2 and then plot it. And we get to see it a little bit better. Okay, so what is happening here is the time passes, so it's time passes, and then the sunflower grows, and the idea is that it grows really fast, and then it reaches a peak, and then it slows down, and then that's how high it's going to grow. And then this height up here is 256. So we can answer the question. Use the graphing calculator to graph the function. Interpret the meaning of the asymptote, which is up here because it gets close to 256 and then it flattens out. It just keeps on going there. And so interpret the meaning of the asymptote. It's the maximum height.